Special systems of equations. So we've been solving systems of equations, two or more equations that are happening consecutively at the same time. We've solved them by graphing, we've solved them by substituting, and we've solved them by elimination using addition and then elimination using multiplication. So now we're going to look at some special systems of equations, and we've seen special solutions before, and this is what they look like in a system of equations. So let's start with this first one. We're going to solve these by graphing. So I'm going to solve this first system, y equals negative 2x plus 5, and y equals negative 2x plus 1. So if I graph these, I want to use slope-intercept. That's going to be easier than making a table. So I'm going to use slope-intercept form here. So my first equation, the y-intercept is 5, and the slope is a negative 2. So I'm going to graph a positive 5 on my y-axis, and a slope of negative 2. So I'm going to go down 2 into the right one, down 2 into the right one, and here's my line. I'm going to graph the second equation, which is y equals negative 2x plus 1. That has a y-intercept of 1 and a slope of negative 2. So I'm going to start here on the y-axis at 1, and I'm going to go down 2 into the right one, down 2 into the right one. And I'm looking for where those two lines intersect. Remember, I'm looking for where they meet each other. But you'll notice that since they have the same slope, they are actually parallel to each other. Since they're parallel to each other, they will never meet, which means there is no solution. So if I'm graphing and I see parallel lines because they have the same slope, that is no solution. Now, we're not always going to solve using graphing. We might use elimination or substitution. So what does the special solution look like if I'm not using graphing? So let's use elimination for this one, because these two equations are set up very similarly to each other. Again, with elimination, I want to have two of the coefficients of one of my terms be opposite each other, so that when I add the two together, we come up with 0. It eliminates that particular variable. So if these two equations, I don't have any coefficients that are opposites of each other. So but I do have some that are very close. So for instance, this is 1y and 1y. So if I multiply one of the equations by a negative 1, I'll have opposites. So I'm going to multiply this first equation by negative 1. So negative 1 times y, negative 1 times negative 2x, positive 2x, negative 1 times 5 gives me negative 5. I'm going to line these two equations up, and again, notice that I've got my y's stacked up, my equal sign stacked up, my x's are stacked up, my addition is stacked up, and my constant is stacked up. So now I'm just going to add down. So a negative y plus a positive y gives me 0, because they're opposites. It's my equal sign. A negative 2x plus a positive 2x also gives me 0. My negative 5 plus positive 1 gives me negative 4. So notice what happened is both of the variables just vanished there, and I ended up with 0 equals negative 4. And this is what we've seen before when we were solving equations and we ended up with these weird solutions. My variables are gone, and I have two numbers that are not equal to each other, so that is my no solution. So a no solution, we can get that through our algebraic methods here of elimination, but I can also see it on a graph. On a graph, I have two parallel lines. So we've got no solution. But we also have one other special solution when we're looking at systems of equations. So let's look at another system. I have y equals 1 half x minus 2, and x minus 2y equals 4. So we're solving by graphing to start with, so let's see what that looks like. Well, my first equation is in slope-intercept form. That's very nice. So y-intercept of negative 2 and a slope of 1 half. So I'm going to graph my y-intercept of negative 2. I'm going to have a rise of 1 and a run of 2. Rise of 1 and a run of 2. There's my line. My second equation isn't so friendly to graph, so I am going to rewrite it so it's in slope-intercept form. So I'm subtracting x from each side. Remember, I'm trying to get the y by itself. I'm going to divide by a negative 2 here to get the y by itself, so I'm dividing everything by negative 2. I come up with y equals 4 times divided by negative 2 is negative 2. A negative divided by negative is a positive, and this is a 1 here in front of this x, so I get 1 half x. So I have y equals negative 2 plus 1 half x. So my y-intercept is negative 2, and my slope is 1 half. Oh, my y-intercept is negative 2, and my slope is 1 half. That is the same description as my first line. So my two lines are actually the same line. But the way they were written, it wasn't so easy to tell that they were the same line. So when I graph these two, one's right on top of each other, which means that any ordered pair that's a solution for one of these equations is also a solution for the other equation, since they're the same. So since I'm describing the same line, any ordered pair that works for one equation also works for the other. So for instance, if I go on the graph here, let's see, 1, 2, 3, 4, and I have 4, 0 is an ordered pair. So if I plug that in there, 4 minus 2 times 0 equals 4. Yep, it works for that one. Let's try it for this one. 1/2 times 4 is 2. 2 minus 2, yep, that's 0. So an ordered pair that works in one also works in the other because they're the same. So we say infinitely many solutions, which means I can't pick any ordered pair that I want. However, there's an infinite number of solutions on that line. So any solution on that line for one equation will also work for the other. So infinitely many solutions. We've seen what it looks like with a graph. What does it look like if I solve this system of equations another way? So let's try substitution since I have the y isolated here. So I'm going to plug in my 1/2 x minus 2 into the other equation. I'm going to substitute that in there. And when I do this out, I end up with 4 equals 4. So notice my variable vanished, x minus x, made that go away. And so I ended up with 4 equals 4. So the variables are gone, and I have two numbers that are equal to each other. 4 equals 4. So this is true. This tells me that I have infinitely many solutions. There are solutions. Any solution on one equation will work for the other. So our special solutions for our systems of equations, these two graphs, if I think of them, one parallel lines with no solution, and the other where they're both the same line, infinitely many solutions.